Section 2 from Chapter 8 focuses on estimating with confidence intervals when your statistic is a proportion or a percent. In this section, we're going to talk about the different things you need to check to make sure you can actually construct a confidence interval, how we can determine the critical z-values so we can get a particular confidence level, and then creating those confidence intervals themselves, as well as doing some algebra to determine a sample size that would be necessary to obtain a certain level of confidence with a specified margin of error. Before you can take information from a sample and make inferences to the population with a proportion, you're going to have to meet 3 requirements. The first is that it has to be a random sample in the first place. So if you have bad sampling procedures, there's underreporting or voluntary response or convenient sampling, and you realize it's not a good random sample, then you're going to say you can't make a confidence interval in the first place. The second piece you need to check has to do with independence. When we're sampling without replacement, we have to check to make sure that the sample number is less than 1/10 of the population number. Otherwise, if that works out to be true, then we can go ahead and calculate the standard deviation using the formula. Otherwise, there's a different formula that we have to use, which we don't learn about. The large counts condition basically says that the number of successes and the number of failures has to be greater than 10, both of those. So you take the proportion and multiply it by the sample size, and the sample size but multiplied by its complement, so that's successes and failures, and they have to be at least equal 10. Once those are met, then we can go ahead and create our complement. So we can use the general formula for section 8.1 to construct a confidence interval when we are looking to make inferences about the population proportion P. And so our statistic in this case is going to be proportion. Our critical value is the z-score that aligns with the confidence level we're interested in, and then the standard deviation of the statistic. Well, here's our standard deviation of a proportion from the population. We use the exact same formula, but we're using p-hat instead of the population proportion because we don't have the population proportion. So this is called the standard error when we're using the sample. So the standard deviation, it says it right here. I was going to repeat myself. There we go. Standard error is when you use the statistic to estimate the standard deviation of the population. Finding a critical value, this one, for example, asks us to look at 95. We've done this several times in class. If 95% is covered by our interval, then that means that there's 5% that's split between these two sides. So we would go ahead and find the z-score for 0.025 or 2.5%, and that would be 1.96. And 1.96 is the critical value for a 95% confidence level. Now when we learned 68, 95, 99.7, we used the number 2, but this is the actual z-score for 95%, so we're going to go ahead and use this as our critical value whenever we decide that our confidence level is going to be 95%. If you already understand how to find the critical value, I'm just going to do it really fast one more time. So 80% is going to leave us 20% on the tails. That means 10% on each tail. We're going to go ahead and look at the table or use inverse norm 10. And so we go to the table, and the closest thing we can get to 10% is 0.1003. Then we read backwards, and then our z-score from here would be negative 1.28. And so we're going to go ahead and use 1.28 as our critical value, which is delineated with that little star, critical Z star. So we've checked to make sure all of our requirements are taken care of. Random, 10%, so we can use the standard deviation formula. We've got large count, so we can go ahead and use z-scores to help us understand because it's approximately normal. So then we can just go ahead and plug things into the formula. So the formula is going to be your sample proportion, the Z that meets your C confidence interval, and then you go ahead and find the standard deviation with the proportion, 1 minus proportion divided by n, which is your sample size. Do that calculation, and you can leave it in this form, which is margin of error form, or you're going to go ahead and calculate it out and give the interval form. So in general, if you want to get a full credit on any free response question on the AP test, you want to follow the state, plan, do, conclude, or answer 4-step process. So in our case, we're interested with confidence intervals. We're specifically, interested in what parameter we want to estimate and what confidence level. So we're going to communicate that at the beginning. We're going to talk about our plan. We're going to explain the method we're going to use and make sure we check the appropriate conditions. If the conditions are met, we're going to go ahead and do it. And it's possible that there'll be a free response question where you'd have to say, it doesn't meet this requirement, so I have to stop. And then you can conclude, you interpret your interval in the context of the problem. So we're going to do one together. So imagine that we had a lot of beads. We have 10,000 beads, and we took an SRS of those beads. There's white beads and red beads, and we got 107 red and 144 white beads. We're going to go ahead and calculate and interpret a 90% confident interval for the proportion of red beads, because we want to see if the teacher's claim that there's 50% of the beads are red is a feasible claim. So we're going to calculate that interval so we can see. So first, we're interested, here's our stating, we are interested in the population proportion of red beads so we can decide if the teacher's claim is feasible. Plan, we're going to calculate the sample proportion, check. 107 out of the 251 are red. Then we're going to check our conditions. We can't do a proportion confidence interval without the following being met. It was a simple random sample, so yes, it's random. 10%, since 10 times 251 is definitely less than the 10,000 beads in the container, we're okay to use a standard deviation formula with the p-hat that we've collected, which is right here. And then the last check is we want to make sure that the number of successes and the number of failures both are greater than 10. So the sample size times the proportion of successes is 107, and the sample size times the proportion of failures is 148, not 148, 144. So check, we meet all three of those requirements. Because we met those requirements, then we can go ahead and use our formula. So we decided we're going to do a 90% confidence formula. Reminder that 90% is going to leave you with 5% on each side. So there we've got 164.5 because it's right in between these two as our confidence level at 90%. So we're going to go ahead and plug our numbers in. We have a 0.426 as our proportion of red. Here's our here's our Z star right there. And then we're going to go ahead and use our P and our 1 minus P divided by 251. So these are the numbers we're going to get. Our center is 0.426, and then our margin of error is plus 0.051 and minus 0.051. So our range is 0.375 to 0.477. So if we want to change that to percents, we've got 37.5 to 47.7. We have a 90% confidence level that the true proportion of reds is between 37.5 and 47.5. If this is true, then this can't really be true. He can't be telling the truth. Since the interval gives us a range of plausible values and 0.5, which is 50%, isn't even in that range, we have reason to doubt his claim. So let's say we're planning a study to make an estimation of about a population parameter, and we want to make sure that our margin of error is not too big. We want a specific margin of error, maybe 2 percentage points above or below the center value. So to do that, we have to make sure we plan a sample size that's big enough. So to determine the sample size, we don't have the proportion population. the population proportion. We don't have an n yet because we haven't figured it out. So how are we supposed to figure this out if we don't have that? There's two things you can do. One is you're gonna do quite a bit of algebra in just a moment. But if you don't know what the p hat is, or you don't have an idea from previous work, when the proportion is 0.5, that's when you're going to end up with the biggest margin of error. So you might as well just use that one. So we're going to use that as an example. So here we are. A company has received complaints about its customer service, and the manager intends to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service, measured on a 5-point scale. Now, the president wants to estimate the proportion of customers who are satisfied. That's either a 4 or a 5. A 4 is satisfied, a 5 is very satisfied. The two highest levels points on the 5-point scale. Now she wants the estimate to be within 3 percentage points at a 95% confidence level. How large of a sample is needed? Well, we need to find, here's our margin of error. They want it to be less than or equal to 3%. And here's our confidence level, and we know that a 95% confidence level is 1.96. But we don't know yet the n, and we don't know yet the p, and if the president hasn't done any previous work with this, then choosing that 0.5 as your proportion to work with is probably the smartest choice. So here we are, here we are, here we are. This is what we're looking for, okay? So we have our z-score, we're going to use our 0.5, and we're going to go ahead and solve the equation. We're going to put it all into the margin of error and do some algebra. Get ready. Okay, so we put our confidence level, our z-star. We're going to go ahead and put 0.5 in for this. Whoops. Now let me start. Okay, so I've plugged in my critical value, I've plugged in my p and my 1 minus p, I've plugged in the margin of error that I want it under. Now we have to solve for n. Bring back your Algebra 2 heads. First thing I'm going to do is I'm going to divide both sides by 0.03, because I'm going to try and get the n on the other side. So I'm going to divide both sides by 0.03, and we get 1.96 divided by 0.03. While I'm at it, I'm also going to multiply, remember this is true, that's true, okay, this is 1. I want to get rid of that square root of n, so I'm going to multiply both sides by square root of n. So I'm going to get the 1.96 divided by 0.03 times the square root of 0.5, 1 minus 0.5 is going to be less than or equal to the square root of n. Now I want to get rid of all of this square rooting, so I'm going to square both sides. So this is going to be squared. This is going to be squared. By the way, I'm just going to put that as 0.5 now. And then this will be squared. So now all we have to do is do the math, because we're trying to find out our sample size. And so our sample size has to be greater than all of this mess. So when we get to this step, we're going to go ahead and do what's inside the parentheses first, and we get 65.3 with a repeater. We're going to square that. We get 4,268 times the 0.25, which is the product of those. And we get this final inequality. Now we're looking for a sample size that will give us some within the margin of error that we want. And so we have to round up to the nearest participant, even though this is lower than traditional rounding rules. We're going to go ahead and round up to 1,068 participants to make sure we're within that 3% margin of error, plus and minus the center point. So here are all the things we need to be able to do, and it's possible that this is right. Okay.